details on undogmatic learnable ontologies. So what's an instrumental reward function? So the nice thing about it is there are like two equivalent definitions. And the way it works is, so we talked about environments. So an environment was, so most naive definition was if an environment is a mapping of the signature, right? But then we said that this is not quite right because, first of all, we want it to be like a partial mapping or the equivalence class of such mappings, and we don't really care what it outputs in histories, and the environment itself assigns probability 0 to them. But also that this is kind of unnatural from the point of view of mixing things. So there's like, yeah, so actually the alternative way we talked about was that we can describe environment as polydistribution, right? So we call it, we have the equivalent definition that like an environment is now just some measure. So we call check a measure on A times O omega, such that for any phi from O omega to A, mu check of C pi equals 1, right? Where C pi is the set of all like destinies that are like consistent with 1. Okay, just have a definition in the beginning. And this is a nicer definition because this thing makes it explicit that there is a convex space of environments. And this is a kind of convex space that has some interesting structure to it, which is just to give like some kind of example, to give some intuition. So suppose we were, so this convex space, I also call it in the post the space of instrumental states, as omega, as you know, in the space of all of those things. And, so I constructed differently, maybe a more kind of convoluted construction, here it's just like a short definition. So, yeah, this is kind of also related to what's called causal states in computational mechanics. But yeah, so like for any n, we can also project it to instrumental states of time horizon n, right? Which is just, so what is this thing? So what is this thing? So this thing is just measures on A times O to the power of n, such that, again, for any I, oh, this is actually supposed to be O star. Right, so this thing is measures on A times O to the power of n. And for E pi, like this, right? So we have or measures also mu hours, mu of C pi n. So literally just the same definition, only we're working with time horizon and instead of infinite time horizon. And there is an arrow from here to here, which just works in the, so the way this arrow works is just like in the obvious way, where like there's a natural mapping here, which is just taking the prefix of length m, right? Graph m, and then this mapping here is just a push forward, right? So when we want to go here, we can send mu to the push forward of mu in this map. We actually have like a sequence, IS0, IS1, IS2, etc. And IS omega is actually the inverse limit of so those spaces and all of those ISNs are polytope actually. This is kind of a little bit interesting because so in the case where we don't have any actions, or there's just one action, so actions are irrelevant, in this case ISN would be just the simplex delta of ON. But in the general case, it's some kind of more interesting polytope. For example, suppose that we have like two actions and two observations, and we want to know what the IS1 is. So IS1 will be like a square in this case, because like on this axis, right, so if I have like two actions, A, B, and let's say I have like two observations, P, Q, right? So I can here, on this axis, I write like the probability of observing E after the action A, and here we can put the probability of observing P after action B. And they're both, so we get like this kind of square. And naturally higher ends will be some more complicated polytopes. So in the first reinforcement learning with imperceptible rewards, I actually define as omega by defining the sequence and then taking the inverse limit. And here you see that we can just define it directly. Yeah, one thing here that's kind of interesting that this is omega is also a compact Polish space, which is kind of obvious from this picture because those are just compact polytopes, so they are compact Polish spaces. And then when you take an inverse limit of the sequence of compact Polish spaces, you get a compact Polish space. You could also directly see from the definition of poly distributions. So you need to define the weak topology. I don't think I actually done this exercise, but I think you can kind of define the weak topology and poly distributions. And all of us need to just kind of define the probability distributions, and it should probably work. But the same key thing here is so now we're ready to give our first definition of what an instrumental reward function is. So our first definition of instrumental reward function. So definition. and instrumental reward function is R, a mapping from is omega to real numbers, which is continuous, and a font, continuous, and a font. Okay, so continuous define functional on the space, we call the instrumental reward function. And okay, what's kind of the intuition here? So the intuition is like we have an agent, right? And kind of the traditional way to do rewards is like the reward is some function of what we observe. Here, the reward instead is a function of what can counterfactually happen in the future. Okay, so it's like, like imagine your agent took some sequence of actions, it's seen some observations, and now, there's some point of time, so what is the reward now? So the reward now depends on what is the probability distribution over things that will happen in the future under all possible follows. This is kind of the idea of this instrumental state. It's kind of a way of assigning the state to the environment without like having some kind of a state space handed to you. It's just like a canonical way to assigning the environment states in terms of like what is observable for particular reasons. So one way to kind of look at it is that it's like the theory of causal states in computational mechanics. That if you have like minimal, it kind of shows up when you're doing like minimal machines. So here it also shows up if you're doing minimal POMDPs. So if you kind of know the theory of finite deterministic automata, there's this classical theory about the minimal automata that decides a particular language is what you get from if it's Myers neurons equivalence relation process. So this is in some sense the equivalent of that for like POMDPs instead of finite deterministic automata. So okay, formally, like if you have so suppose that we have some POMDP. So let's consider we have some POMDP. So again, we have some state space, some initial state, right? And we have like a transition kernel, which takes a state in an action and outputs a distribution of where the next state is. So actually, let's say it outputs a distribution over the next state of observation. So maybe I used like a different notation previously, but this is like an important form. It's more convenient in this case. So plane.
Now I have a question about the general definition. So if you have utility function on destinies, does it give rise to an instrumental reward function by integrating against
Not really. How would you define instrumental reward function on destinies?
Like if IS omega is measures on destinies or polymeasures, you can integrate against the
integrate the poly distribution against the utility function.
Yeah.
So I think that would usually diverge because, like, okay, like, let's see. So if you kind of integrate, if you do something like integral of some utility function or whatever times pi c pi, the characteristic function of c pi, times mu of, oh geez, the bad notation. That's mu of dx, right, over destiny. Then this is equal to the expectation with respect to pi, like utility, right? But if you're doing it without this thing, then it's something like, it's not exactly, but it's kind of like you're summing over all possible policies. Not quite, because they kind of overlap with each other, but so for example, yeah, so it feels pretty divergent in HT. Yeah. Maybe so. Okay, actually, I haven't thought about it from this angle. This might actually be useful because so this is like a fine function of those things. So it feels almost necessary that it should be possible to write it as an integral, right? But well, I mean, yeah, like if this is your utility function, for example, then it's integrated, right? If you have like a linear combination of things of this form, then it integrates. So yeah, so okay, so you could have, so yeah, there is a sense in which you can start with a utility function of destinies and get an instrumental reward function, but it has to be like a particular type of utility function of destinies, which I don't know how to characterize at the moment. But this is actually an interesting problem to characterize. To give a characterization of this in terms of integrals. It seems like it should be doable. I don't know what the answer is. Yeah, but then the semantics, but even so, the semantics is still pretty different from when you consider this to just be a utility function over destiny. Because like utility function over destiny means that okay, this is kind of what destinies you like. This is more like, at every point of time you consider, so this is not even a utility function, it's a reward function, which you kind of do a time discounted sum. So it's like at every point of time you want the destiny going forward to be something, and something more weird. But anyway, it's an interesting problem. Okay, so going back to this, so given a POMDP, there is a canonical mapping. Yes. So, okay, let me maybe even do it slightly differently. So we have this notion of POMDPs. Now, notice that I's omega itself is a huge POMDP. Right? So we have like, well, it doesn't have an initial state, but it does have like a transition kernel. Because there is some kind of mapping of T, from let's call it T, I don't know, how to call this, T universal or something, T uni, from I as omega times A to, well, it's not exactly, I mean, it's something like a distribution over I is omega times A. Like, it's not exactly true because a lot of those things are kind of redundant shit. It's more like something, like what I want to say here is it feels more like I is omega tensor A. So, okay, I won't try to make this precise, but so there is a sense in which I is omega is kind of almost like a terminal object in the category of POMDPs. So not quite, but maybe that's some way to phrase it. But the claim is like this: for any POMDP, there is a canonical mapping. Canonical mapping phi from the state space of the POMDP. Well, we don't even need the initial state, doesn't it? It only depends on T, right? QIS POMDP. Any POMDP is canonically embedded inside this IS POMDP. Because for any state, it can be like, okay, suppose I set this state to be the initial state. What is the environment this POMDP defines? Right? Like every POMDP gives rise to an environment, so it's an element of IS omega. So if I set a particular state as the initial state, it gives rise to a particular environment, so a particular element of IS omega. So hence we have a mapping from S to IS omega. So every POMDP is like uniquely embedded here. And moreover, if we look at the image, if some two states go to the same state, then it means that they are essentially equivalent. And if we look like at so it's more than that. Like it's if we have like two states here that go to the same state here, then it means that they are, for all practical purposes, the states behave absolutely the same. So we can always kind of replace this whole space by its image. But there is actually something stronger than that, because suppose that there are some free states S1, S2, S3, such that phi of S3 is equal to some convex combination of phi of S1 plus phi of S2. Then S3 is also a redundant state. Like every time we go to S3, we can instead flip a coin with probability p minus p to draw one of those two states. So, so we can kind of, by this way, get a kind of recipe for what, starting from a POMDP, getting like a minimal equivalent POMDP, by just kind of, okay, so what the recipe is actually. Okay, so we have this POMDP, we have this mapping, and now what? So now let's look at the convex hull of the image of S under this mapping. And in this convex hull, there are some extreme points, right? So let's call it Q, B, the extreme points in the because then there is a POMDP with state space Q, which is equivalent. To the original POMDP. And yeah, I'm not sure there's a way to make a formal claim to this minimums and such, because there might still be a way to make an even smaller POMDP if, like, for example, this Q, it looks like 4 points on a plane, and maybe if we choose 3 points here and have some triangle which contains this, and represent those as like honest variations of the breaks of the triangle. So yeah, it's not quite right to say that it's minimal. So I think there's probably some theory that's like minimal for theory that allows you to do this, but I'm not immediately sure how to state it. So here's obviously something on the slides. Yeah, I guess, okay, yeah, I guess what we could do is look at the affine valve of this, and yeah, but then, yeah, I don't know what to say, but I just want to convey to say, yeah, this kind of mapping allows you to kind of simplify POMDPs by going to this space of where like all the states are defined because they're actually information. Okay, so we have one definition of instrumental regard function. There is also a second equivalent definition. Okay, so we consider some notion of like some experiments that we can conduct, which will terminate in a finite number of states. So okay, so let's which letter should we use? Sine. So psi is going to be some mapping from A times O star to distributions over actions is joint union with the volume. So what is this thing? So think of it as like a policy, like a stochastic policy. If you follow for some time until it outputs the symbol bottom, which means the experiment ended. Okay. So you're and we wanted to have the property that the experiment always ends with probability 1. So the property is like, like for any, so we require that like for any new that we can let us interact with, if we consider like mu psi, then this is basically supported on, so mu psi would be like in general some distribution in like yeah, on what? On A times O smaller equal to 1. Right? If you interact with the sign, you get some sequence of actions and observations that might go on forever, but may also stop somewhere, because sign outputs a stop signal. But we are interested only in the case. So we require that the support of new sign is in fact it's just finite. Okay, so this is like another way of saying that no matter what the environment is interacts with, there's probability 1 that it will finish eventually. Okay. So this kind of a way, you should think of it as kind of some experiment that the agent can decide what to do. So now, suppose that after seeing the result of the experiment, we assign to the result some score. So we have like some kind of an R0, which is just the mapping from A times O star to real numbers. Like the score, you see kind of the result of history that kind of came out of the experiment and send it to the numbers. So now imagine that you kind of conduct the experiment psi and then measure R0 and take the expected value of this thing, right? Then this defines us. So for every psi in R0, we get some R from instrumental states to R. How? Because simply R of a particular instrumental state mu is by definition take the expectation with respect to mu psi of R0. Okay? And now there's a theorem that the R above is continuous and fine, and 2, any R like this, which is continuous and fine, is fine is of this form. And we also have it bounded. Okay, so those are basically two equivalent ways to talk about instrumental Y function. One is just a continuous affine function of space of instrumental state. Another is in terms of like there's some experiment I can do, such that I give some score to the result, and the score is an unbiased estimator of like whether we regard this. If we take the expected value, then this is very important. And those two are equivalent, and this is actually, I mean, it's not super difficult, but it actually needs to do a little work. Okay, so those are instrumental work functions. And now, the upshot of this whole story is that we can do learning with those instrumental reward functions. This kind of reward function is actually learnable under these usual assumptions. So basically the claim is just that all the hypothesis classes we had before that are learnable are going to be learnable in this framework also. Okay, I haven't really explained something. So what does it mean to do? So notice that from an instrumental reward function, you can construct a utility function in the usual way, right? Like if you have, like imagine your agent is like interacting with the environment. So essentially in any time step, there is some instrumental. Okay, so let's write it down. So suppose, let mu be an environment, right? And so we consider some finite history. So let H be some element of A times O star, which is the history so far. Then we can do mu conditional on H, which is like the environment starting from this point. And this is also going to be some element of IS combinator. Right? Just kind of the environment starting from this history. So now, if I have like, if my mu interacts with some policy, so now if I have some policy phi, it's like fourth policy, then I can consider like the expectation with respect to mu phi of what? So now I can do a side expanded sum. So 1 minus gamma, sum, n equals 0 to infinity, gamma to the power of n. And now I need the instrumental one. So what is the instrumental one? It means I take r of mu of the history so far. Right? This is like the destiny. So I take the prefix of length n of this destiny. And this is this is kind of the expected utility in this framework. Where R is the instrumental reward function, right? So R is an instrumental reward function, so it's like mapping some continuous finite like this. Yeah, notice the unconventional form of this thing, because mu appears here, but it also appears here. And this is different from how we did in the conventional observable framework things. The conventional observable frameworks, I would just write R of D. There would be no mu here. So it's kind of different kinds of methodology. So, okay, so given this notion of expected utility, I can also define that regret and learnability and everything else is defined the same. But this is kind of my notion of expected utility. And the upshot is that we have the same kind of learnability results. So we have to actually improve it for communicating POMDPs, but I'm pretty sure that if you take down communicating RDPs or POMDPs or whatever, then all of those classes will be learnable in this sense. Yeah. So here the claim is like if we take like all like communicating MDPs, RDPs, POMDPs, and this is going to be still a learnable class. So actually only have the proof written for this, and I also have a red now, but I think it should be straightforward. So there was also this notion of semi-instrumental reward function. it's like some R which depends on the history, but also on this potential state. And that which is H01, and it's like continuous defined, it's like continuous, continuous, and defined in the second part. And so this kind of a hybrid of both approaches. So in here you can just write the same expression here, but also insert the history, right? So here a notion of expected utility is expectation of D linear farm, 1 with the scalar, sum, n equals 0 to infinity. And so here it can be both. So for those things, I think it's also pretty straightforward to have like some basic learnability results along these lines. So we need to be more careful here. For example, we need, because this R itself has to like not have irreversible kind of transitions inside of it. So previously we had the notion of reward machines. So I think we can we can maybe try to do the exercise some other time, but I think we can extend the definition of reward machines to like semi-instrumental reward machines, and then have some theory of this form.